Picture our beautiful blue planet, a vibrant orb swirling with clouds and vast, shimmering oceans. From the gentle glow of dawn to the serene blanket of night, it appears as a familiar haven, a world thoroughly explored on its surface. Yet, what if the true extent of Earth's water wasn't visible from space, hidden instead far beneath the surface, locked away within solid rock? Could our world, which appears so intimately known, actually harbor secrets about water that dwarf even its magnificent surface seas, holding an entire hidden ocean within its stony heart? This remarkable possibility invites us on a journey not across the stars, but deep within our own home, into the hidden depths beneath our feet. It's a journey into a realm of immense pressure, unimaginable heat, and startling discoveries that redefine our understanding of the planet we inhabit. Let's gently descend, layer by fascinating layer, peeling back the veils of rock and metal to uncover the true nature of Earth's interior, a place far more dynamic and mysterious than most of us ever imagine. Imagine the sheer volume of water contained in all Earth's oceans, a staggering 1.35 billion cubic kilometers, enough to cover the entire globe to a depth of 3.7 kilometers. It shapes our weather, sustains life, and defines our planet as the blue marble. But what if there was an equal or even greater amount of water not flowing freely, but chemically bound within minerals thousands of kilometers beneath the surface, under pressures that would crush any conventional submarine? How could such a monumental reservoir remain largely out of sight? And what does its existence imply about the very processes that govern our living world? This is a question that challenges our preconceived notions and opens up a new frontier of exploration, not outward, but inward. Our planet is structured much like an onion, composed of distinct layers, each with its own unique properties, composition, and role in the grand geological symphony. At the very surface lies the crust, our familiar home. This is an astonishingly thin shell, akin to the skin of an apple compared to the fruit's entire volume. It's the layer we walk upon, where mountains rise majestically into the sky, where deep ocean trenches plunge into darkness, and where all life as we know it thrives. This outermost layer varies in thickness, from a mere 5 to 10 kilometers beneath the vast oceans, where it is known as oceanic crust, to a more substantial 30 to 70 kilometers under the towering continents, forming the continental crust. Despite its relative fragility and thinness, this is the dynamic stage for all geological activity visible to us. The shifting of tectonic plates, the rumble of earthquakes, the fiery breath of volcanoes. It is a world of constant change, yet it represents only a tiny fraction, less than 1%, of Earth's total volume. Beneath this relatively fragile skin lies the mantle spheroids, a colossal layer that accounts for about 84% of Earth's total volume and approximately 67% of its mass. Extending from the base of the crust down to a depth of about 2,900 kilometers, the mantle is a vast rocky realm that, at first glance, might seem like an impenetrable solid. Yet, this is no ordinary rock. Under immense pressures and temperatures ranging from a few hundred degrees Celsius near the crust to over 4,000 degrees C at its deepest reaches, the mantle behaves like a very thick, slow-moving fluid over geological timescales. Imagine a substance that feels solid to the touch, but over millions of years flows and churns with the power of a mighty river, driving the movement of continents across the planet's surface. This slow, convective motion of the mantle is the engine behind plate tectonics, shaping our world in ways we can only begin to comprehend. And within this deep, hot, and slowly churning rock scientists are finding compelling evidence for hidden oceans, not of liquid water, but of water bound within the very crystal structures of its minerals. What an extraordinary thought! Vast quantities of water, not as a flowing sea, but as an integral part of the rock itself. Deeper still, beyond the mantle's incredible expanse, lies the Earth's core, the mysterious heart of our planet. This region, starting at about 2,900 kilometers below the surface and extending all the way to the very center at approximately 6,371 kilometers, is a place of truly alien conditions. It is primarily composed of iron and nickel, metals that are incredibly dense and subjected to pressures and temperatures that defy easy comprehension. The core itself is divided into two distinct parts: the liquid outer core and the solid inner core. The outer core is a swirling, incandescent ocean of molten iron and nickel, extending from 2,900 to 5,150 kilometers deep. Here, temperatures range from 4,400 degrees C to 6,100 degrees C, hot enough to melt these metals completely. This dynamic, electrically conductive fluid is in constant turbulent motion, generating powerful electrical currents. These currents, in turn, create the Earth's magnetic field, a vital shield that protects our planet from harmful solar radiation and cosmic rays, making life on the surface possible. Without this invisible force field, our atmosphere would likely be stripped away, leaving Earth a barren, lifeless world. It's a testament to the profound interconnectedness of Earth's layers that this deep, unseen engine has such a direct and critical impact on everything we perceive on the surface. Then, at the very center of it all, lies the Hati et inner core, a solid sphere of iron and nickel, roughly 1,220 kilometers in radius, about the size of the Moon. Here, the temperatures are even more extreme, estimated to reach an astonishing 5,700 degrees. To put that into perspective, this is approximately the same temperature as the surface of the Sun. Yet, despite this intense heat, the inner core remains solid. How can something so incredibly hot not be molten? The answer lies in the equally unimaginable pressure exerted by the overlying layers. At the Earth's center, the pressure reaches an astounding 3.6 million atmospheres. This colossal force compacts the iron atoms so tightly that they cannot move freely, forcing them into a solid, crystalline structure, even at temperatures that would instantly vaporize any material on the surface. This is a state of matter unlike anything we typically encounter in our daily lives, a paradox of extreme heat and extreme rigidity. So, here we are, contemplating a planet with layers of unimaginable heat and pressure, where water can be locked in rock and a core hotter than the Sun's surface remains solid. But how do we know any of this? Direct exploration of these depths is, for now, beyond our technological capabilities. The deepest human-drilled hole, the Kola Super Deep Borehole in Russia, reached a mere 12.2 kilometers, barely scratching the surface of the crust, a fraction of the way to the mantle, let alone the core. The heat and pressure quickly become insurmountable obstacles, melting and crushing our instruments. This leads us to one of the most remarkable achievements of modern science, peering into the inaccessible. How can we map these hidden layers, deduce their compositions, and understand their dynamics without ever directly touching them? What ingenious methods have scientists developed to unravel the secrets of a world that remains stubbornly out of reach? The answers lie in listening to the planet itself, interpreting the subtle whispers and powerful reverberations that travel through its very fabric. This journey into Earth's core is not just about physical layers. It is also a testament to human ingenuity and our relentless quest to understand the fundamental workings of our home. It's a story of indirect observation, meticulous deduction, and the continuous refinement of our models, pushing the boundaries of what we thought was knowable about our own planet. The revelations waiting for us within the Earth's hidden depths are profound, shaping our understanding of everything from plate tectonics to the very habitability of our world. As we gently descend from the familiar crust, passing the deepest mines and the roots of mountains, a profound transformation begins. The solid, brittle rock we know gives way to something vast, dynamic, and truly alien: Earth's mantle. This immense layer, stretching for nearly 2,900 kilometers beneath our feet, makes up an astonishing 84% of our planet's total volume. Imagine a journey from one side of a continent to the other, not across the surface, but straight down into the very heart of the Earth. That gives a sense of the sheer scale of this enigmatic realm. Here, temperatures steadily rise, from around 500 degrees Celsius near the crust to a scorching 4,000 degrees Celsius at its boundary with the core. The pressure, too, becomes immense, reaching millions of times that at the surface. Yet, despite these extreme conditions, the mantle is not a static, inert mass. It is a slowly churning, viscous solid, flowing over geological timescales, driving the very movement of our continents above. But what if this vast, rocky interior, far from the sun's warmth and the open air, held a secret even more astonishing than its fiery heat and unimaginable pressures? What if, within this seemingly arid realm of rock, there lay hidden oceans, perhaps even larger than all the surface water we cherish? This is not a fanciful tale, but a profound hypothesis emerging from decades of meticulous scientific inquiry. The water we speak of is not sloshing in vast underground caverns, nor flowing in subterranean rivers. Instead, it is locked away, deep within the very crystal structure of specific minerals, bound within the rock itself, a testament to Earth's extraordinary chemistry. The key to this subterranean aquatic world lies in a remarkable mineral known as ringwoodite. To understand ringwoodite, let's first consider olivine, a common greenish mineral found in the upper mantle. As pressure and temperature increase with depth, olivine undergoes a series of transformations, changing its atomic arrangement to become more compact and stable under the crushing forces. One of these transformations occurs in a region known as the transition zone, nestled between approximately 410 and 660 kilometers beneath the surface. Here, olivine transforms into wadsleyite and then deeper into ringwoodite. These are what scientists call high-pressure polymorphs, the same chemical composition, but with atoms arranged differently, like carbon forming both soft graphite and hard diamond under different conditions. Ringwoodite, specifically, possesses a unique crystal lattice, a molecular cage, that can accommodate components of water, not as whole water molecules, H2O, directly inserted, but rather as hydroxyl groups, OH, where oxygen and hydrogen atoms become chemically bonded within the mineral structure. Think of it less like a sponge soaking up water, and more like baking water directly into a cake, where the water's components become an integral part of the final structure. This molecular incorporation allows ringwoodite to hold a surprising amount of water, up to 1 to 3% of its weight. While this percentage might seem small, the sheer volume of the transition zone, spanning hundreds of kilometers in thickness and encircling the entire planet, makes this a potentially enormous reservoir. Consider the numbers for a moment. All the oceans, seas, lakes, and rivers on Earth's surface contain approximately 1.3 billion cubic kilometers of water. Now, if the transition zone, a global shell roughly 250 kilometers thick, were to contain even a modest percentage of ringwoodite saturated with just 1% water by weight, the total volume of water locked within this deep earth mineral could easily equal, and quite possibly exceed, the total volume of all surface oceans combined. Imagine that for a moment. Our blue planet might be blue not just on the outside, but also in its very heart, holding a hidden, vast and ancient water supply. How does this profound discovery reshape our understanding of Earth and its long-term habitability? The conditions necessary for water to be stored in such an unexpected way are truly extreme. The immense pressures within the transition zone, reaching up to 23 gigapascals, that's 230,000 times atmospheric pressure at sea level, prevent the incorporated water components from simply turning into steam, even at temperatures exceeding 1,400 degrees Celsius. These staggering pressures force the atoms into a compact arrangement, making the ringwoodite structure stable and capable of holding the hydroxyl groups within its lattice. The high temperatures, paradoxically, are also crucial. They provide the energy needed for the chemical reactions that allow water's components to bond with the mineral structure and for the mantle rock to slowly convect, facilitating the movement and eventual incorporation of water-bearing materials. This deep earth water is not static. It is part of a grand slow-motion hydrological cycle that operates over millions of years. At subduction zones, where one tectonic plate dives beneath another, ocean water seeps into the descending oceanic crust. As this crust plunges deeper into the mantle, the minerals within it become progressively dehydrated, releasing their water. However, under specific conditions of pressure and temperature in the transition zone, this water can then be reincorporated into newly forming high-pressure minerals like ringwoodite. It's a dynamic equilibrium where water is constantly being recycled between the surface and the deep interior, influencing the very processes that shape our planet. But how do scientists uncover such profound secrets from a realm utterly beyond our direct reach? No drill can penetrate kilometers into the mantle, nor can probes withstand the crushing pressures and searing temperatures. Our primary window into these hidden depths comes from the study of seismic waves. These are the vibrations generated by earthquakes, which travel through Earth's interior, much like sound waves travel through air or water. By carefully analyzing how these waves change, speed, reflect, and refract as they pass through different layers, seismologists can effectively create a three-dimensional map of our planet's internal structure and deduce the physical properties of the materials within. Specific anomalies in seismic wave behavior within the transition zone provided the first tantalizing clues. Scientists observed that seismic waves would sometimes slow down or be attenuated, lose energy, in ways that couldn't be explained by dry rock alone. These observations suggested the presence of something that altered the rock's properties, something consistent with the presence of water. Imagine tapping on a solid wall versus a wall with a hidden cavity or a water pipe. The sound would be different. Similarly, the sound of seismic waves changes when they encounter rock with chemically bound water. The most compelling direct evidence for mantle water came in 2014, with the discovery of a microscopic piece of ringwoodite embedded within a diamond. This diamond, found in a riverbed in Brazil, was a true geological treasure, a messenger from the deep. Diamonds are exceptional because they form at extreme depths and pressures, often carrying tiny inclusions of other minerals from their birthplace. The ringwoodite inclusion, measuring just a fraction of a millimeter, contained water in the form of hydroxyl ions, unmistakably confirmed through advanced spectroscopic analysis. This tiny, precious speck of mineral, brought to the surface by volcanic activity, provided the first undeniable physical proof that water is indeed locked within the Earth's mantle. It was like finding a single drop of water, yet it confirmed the existence of a vast, hidden ocean. This understanding profoundly changes our view of Earth. For a long time, the mantle was largely considered a dry, rocky layer. Now, we see it as an active participant in Earth's water cycle, a colossal reservoir that could have significant implications for how our planet works. For instance, water plays a crucial role in lowering the melting point of rocks. This means that even a small amount of water within the mantle can influence where and when magma forms, impacting volcanic activity and the very mechanics of plate tectonics. The presence of water might also affect the viscosity of the mantle, essentially how easily it flows, thereby influencing the speed and nature of continental drift. This deep Earth water cycle also raises fascinating questions about the very origin of Earth's surface oceans. Was all our planet's water delivered by comets and asteroids from space? Or did a significant portion of it emerge from within the Earth itself, slowly outgassing from the mantle over billions of years? The answer is likely a combination of both, but the realization that our planet could have always held its own internal water supply profoundly impacts our understanding of Earth's formation and its long-term habitability. It suggests that the presence of water, a fundamental ingredient for life, might be more intrinsically linked to the planet's internal processes than previously thought. There are still many unanswered questions and active debates in the scientific community. While the existence of mantle water in ringwoodite is now established, quantifying its exact global volume remains a significant challenge. Estimates vary widely, depending on the assumed concentration of water in these minerals and the proportion of the transition zone thought to contain them. Scientists are also investigating whether the water is evenly distributed or concentrated in specific regions, perhaps being more abundant under areas where oceanic plates are actively subducting. Future research, involving more refined seismic imaging techniques and advanced laboratory experiments that simulate mantle conditions, will continue to shed light on these profound mysteries. The journey into Earth's mantle reveals a planet far more complex and dynamic than meets the eye. It is a world where oceans can be hidden within stone, where extreme pressures and temperatures dictate the very state of matter, and where processes unfolding hundreds of kilometers beneath us profoundly influence the surface world we inhabit. Our understanding of Earth is constantly evolving, revealing new layers of wonder and challenging our preconceived notions of what a planet can be. The story of Earth's deep water is a testament to the power of scientific inquiry, allowing us to glimpse the invisible and understand the forces that truly make our planet unique. As we journey deeper beyond the mantle's vast rocky expanse and its hidden watery minerals, the Earth undergoes another dramatic transformation. Below approximately 2,900 kilometers from the surface, the solid rock of the lower mantle gives way to a realm of unimaginable heat and pressure, a place where the very ground beneath our feet ceases to be stone and transforms into a swirling ocean of molten metal. This is the Earth's core, a region so remote and extreme that it remains one of the greatest scientific frontiers, a world within our world, operating under its own profound rules. Imagine a descent into this alien landscape. The pressure, already immense at the base of the mantle, continues to climb, reaching levels that would instantly crush any known material on the surface. The temperature, too, escalates, far beyond anything we experience or can even easily replicate. Yet, within these extremes, the core is not a uniform mass. It is a layered structure, much like an onion, divided into two distinct parts: the liquid outer core and nestled at its very center, the solid inner core. Each layer plays a pivotal yet distinct role in shaping our planet and sustaining life on its surface. Let's first plunge into the liquid outer core, a vast incandescent ocean of molten iron and nickel. This layer stretches for an astonishing 2,300 kilometers, from the core mantle boundary down to a depth of roughly 5,200 kilometers below our feet. Here, the temperatures range from an estimated 4,400 degrees C at its upper boundary, just below the mantle, to a scorching 6,100 degrees C at its deepest point, where it meets the inner core. To put this into perspective, 4,400 degrees C is hot enough to instantly vaporize most rocks, and 6,100 degrees C is comparable to the surface temperature of the sun. Despite this intense heat, the iron and nickel remain liquid due to the equally immense pressure, which ranges from approximately 135 gigapascals GPa at the top to 330 GPa at the bottom. A gigapascal is a billion pascals, and 135 GPa is equivalent to about 1.35 million times the atmospheric pressure at sea level. What truly makes this liquid outer core extraordinary is its dynamic nature. It is not a static, inert pool of molten metal. Instead, it is a furiously active, slowly churning cauldron where convection currents majestically flow. Hotter, less dense liquid iron and nickel rise towards the cooler mantle, release some of their heat, and then, becoming denser, slowly sink back down towards the inner core. This continuous, majestic circulation creates vast, spiraling currents within the electrically conductive molten metal. Think of it like a colossal slow-motion lava lamp, but powered by thermal energy and immense planetary forces, not a simple light bulb. This ceaseless motion of conductive liquid metal is the secret behind one of Earth's most vital features, its protective magnetic field. This intricate process is known as the geodynamo. As the molten iron and nickel flow and swirl, they generate electric currents, and according to the principles of electromagnetism, moving electric currents create magnetic fields. The Earth's rotation plays a crucial role in organizing these chaotic currents, twisting them into immense helical structures. The Coriolis effect, the same force that influences weather patterns and ocean currents on the surface, acts upon these deep-seated liquid metal flows, causing them to spiral and align, reinforcing the magnetic field they generate. It's a self-sustaining feedback loop. The movement creates a magnetic field, and that field, in turn, influences the movement of the conductive fluid, maintaining the dynamo. Could a hidden engine deep within our world truly protect all life on its surface? The answer is a resounding yes. The Earth's magnetic field, generated by this geodynamo, extends thousands of kilometers into space, forming a protective bubble known as the magnetosphere. This invisible shield deflects harmful charged particles streaming from the sun, known as the solar wind, as well as high-energy cosmic rays from deep space. Without this magnetic field, these energetic particles would constantly bombard our atmosphere, stripping away its lighter gases over geological timescales and exposing the surface to dangerous radiation. Life as we know it, with its delicate molecular structures, might never have evolved, or certainly would not thrive, without the constant protection offered by this deep Earth dynamo. It is a profound realization, that the churning, fiery heart of our planet is directly responsible for the habitability of its surface. But what fuels this incredible process? The energy for the geodynamo comes from two primary sources. Firstly, the gradual cooling of the Earth's core over billions of years releases heat. Secondly, and perhaps more importantly, the inner core is slowly growing. As the liquid outer core cools and solidifies at the boundary with the inner core, latent heat is released. Imagine water freezing into ice. It releases energy. Similarly, as molten iron crystallizes onto the solid inner core, it releases heat, which then drives the convection in the outer core. Furthermore, the crystallization process preferentially incorporates iron into the solid inner core, leaving the remaining liquid outer core slightly enriched in lighter elements. These lighter elements are less dense, and their buoyancy also contributes to the convective flow, a process called compositional convection. This intricate dance of heat and motion in the outer core is not entirely stable. Over geological timescales, the Earth's magnetic field can weaken, drift, and even completely reverse its polarity, meaning that compasses would point south instead of north. Such geomagnetic reversals have occurred many times throughout Earth's history, with the most recent full reversal happening about 780,000 years ago. While the exact mechanisms are still being studied, these reversals are a natural part of the geodynamo's long-term behavior, posing no immediate threat to life, though they might affect navigation and satellite communications during the transition period. What astonishing forces are at play to maintain such an impossible balance, and how do we even begin to understand them? Our journey continues, deeper still, to the very center of our planet, where we encounter the solid inner core. This spherical body, with a radius of approximately 1,220 kilometers, is roughly the size of the Moon. It begins at a depth of about 5,200 kilometers and extends all the way to Earth's absolute center at 6,071 kilometers. Here, the conditions defy easy comprehension. The inner core is composed primarily of solid iron, with a small percentage of nickel and possibly trace amounts of lighter elements. And now for the ultimate paradox. Despite temperatures soaring to an estimated 5,700 degrees, a figure often cited as hotter than the surface of the sun, the inner core remains stubbornly solid. How can something be hotter than the sun's surface, yet remain solid? The answer lies in the truly overwhelming pressure. At the Earth's center, the pressure reaches an unimaginable 3.6 million atmospheres, or 360 GPa. To grasp this scale, imagine stacking 100 Empire State Buildings on a single thumbnail. That's roughly the force exerted on every square centimeter at the inner core. This colossal pressure literally squeezes the iron atoms so tightly together that they are forced into a solid, crystalline structure, overriding the immense thermal energy that would otherwise melt them. The melting point of iron, like many materials, increases dramatically with pressure. At these extreme conditions, iron requires an even higher temperature to transition into a liquid state than the already searing heat present. This solid inner core is not a static object either. Seismic studies have revealed that it rotates slightly faster than the rest of the planet, by about 0.2 to 1 degree per year relative to the mantle. This differential rotation is likely influenced by the geodynamo in the outer core and the magnetic forces acting upon the inner core. Furthermore, the inner core itself might not be entirely uniform. Evidence suggests it possesses anisotropy, meaning seismic waves travel through it at different speeds depending on their direction. This could indicate preferred crystal orientations within the iron, or even a more complex layered structure within the inner core itself. The inner core is also slowly growing, albeit at an incredibly slow rate of perhaps a millimeter per year. As the Earth gradually cools, the molten iron and nickel of the outer core crystallize onto the surface of the inner core. This process, as mentioned, is a key driver of the outer core's convection, and thus the geodynamo. The inner core, therefore, represents a geological time capsule, growing steadily since the Earth first cooled enough for its core to differentiate into liquid and solid components billions of years ago. For humanity, the existence and behavior of the Earth's core are not just abstract scientific curiosities. The magnetic field, born from the outer core's movements, is indispensable for our technology. It protects satellites, power grids, and communication systems from solar storms. It also plays a subtle role in animal navigation, guiding species from birds to sea turtles. Understanding the core's dynamics helps us predict changes in the magnetic field, which is vital for long-term planning, whether for space missions or the resilience of our infrastructure. And what profound implications does this inner world hold for the future of our planet? The continued operation of the geodynamo is critical for maintaining Earth's atmosphere and habitability over geological timescales, a silent guardian deep beneath our feet, constantly working to preserve the conditions necessary for life. We have journeyed deep into the Earth, exploring its vibrant, shifting mantle, where oceans of water might lie hidden within stone, and descending further still into the scorching heart of our planet, a core hotter than the surface of the sun, yet held solid by unimaginable pressure. But how can we possibly know any of this? How do we map these inaccessible depths, thousands of kilometers beneath our feet, when the deepest humanity has ever drilled is a mere 12 kilometers, barely scratching the surface of the crust? Imagine trying to understand the intricate workings of a clock by only being able to touch its outermost casing, never peering inside. It seems an impossible task, a profound mystery. Yet, through ingenious scientific detective work, we have managed to create a surprisingly detailed picture of our planet's interior, a feat of human intellect and technological prowess that allows us to see the unseen. The key to unlocking Earth's hidden secrets lies in the very ground beneath us, specifically in the vibrations that ripple through it. When an earthquake strikes, it unleashes powerful waves of energy, much like dropping a stone into a pond sends ripples outwards. These are called seismic waves, and they are the primary tool scientists use to probe our planet's internal structure. Think of them as Earth's own natural ultrasound or X-ray machine. Just as medical imaging uses waves to create pictures of the body's internal organs, seismologists use earthquake waves to create images of Earth's interior. There are two main types of seismic waves that are particularly useful for this purpose. The first are P waves, or primary waves. These are compressional waves, meaning they travel by pushing and pulling the material they pass through, much like sound waves moving through air. P waves are the fastest seismic waves, typically traveling at speeds of 6 to 13 kilometers per second through Earth's rocky layers, and they can pass through both solids and liquids. The second type are S waves, or secondary waves. These are shear waves, meaning they move material from side to side, perpendicular to the direction of wave travel. S waves are slower than P waves, typically moving at 3.5 to 7.5 kilometers per second, and crucially, they can only travel through solid materials. They cannot propagate through liquids. This fundamental difference between P and S waves provides a critical clue about the state of matter deep within our planet. As these seismic waves travel through Earth, their speed and direction change depending on the properties of the material they encounter. If a wave moves from a less dense material to a more dense material, it will speed up. If it encounters a warmer, less rigid material, it will slow down. These changes are not unlike how light bends or refracts when it passes from air into water, or how sound changes when it moves from air into a solid wall. By meticulously measuring how long it takes for these waves to travel from an earthquake's origin to various points on the surface, scientists can deduce the density, temperature, and even the phase state, solid or liquid, of the Earth's interior. This is a monumental task requiring a global network of incredibly sensitive instruments. These instruments are called seismometers. A seismometer is essentially a device designed to detect and record ground motion. Early versions were relatively simple, often involving a suspended weight that would remain still while the ground beneath it moved, allowing a pen to draw the motion on a rotating drum. Modern seismometers are far more sophisticated, employing advanced electronics and digital sensors that can detect ground movements as small as a fraction of a millimeter. Thousands of these seismometers are deployed across the globe, forming a vast, interconnected network. When an earthquake occurs anywhere on Earth, its seismic waves radiate outwards, reaching these stations at different times, depending on their distance from the epicenter and the paths they took through the planet's interior. Imagine an earthquake striking off the coast of Japan. The seismic waves would travel through the Pacific Plate, then plunge deep into the mantle, traverse the core, and eventually emerge on the other side of the planet, reaching seismometers in Europe or Africa. Each seismometer records the arrival times of the P waves and S waves, as well as their amplitudes and frequencies. By combining data from hundreds, even thousands of these stations, scientists can reconstruct the wave's journey, almost like reverse engineering a complex puzzle. This collective data allows them to create a detailed map of the subterranean landscape the waves have traversed. But what patterns do they look for in this vast amount of data? One of the most powerful insights comes from observing how seismic waves reflect and refract at the boundaries between different layers within the Earth. When a seismic wave encounters a sudden change in material properties, like moving from the solid crust to the denser mantle, or from the solid mantle to the liquid outer core, part of its energy is reflected back, and part is refracted or bent as it continues onward. These reflections and refractions act like echoes, providing clear signals of distinct boundaries. By analyzing the arrival times of these reflected and refracted waves, scientists can pinpoint the exact depths of these internal layers. Consider the concept of shadow zones. These are areas on Earth's surface where certain types of seismic waves are not detected, or are detected with significantly reduced intensity after an earthquake. The existence of these shadow zones was one of the earliest and most compelling pieces of evidence for Earth's layered structure. For instance, S waves create a large shadow zone on the side of the Earth opposite an earthquake. This is because S waves cannot travel through liquids. Therefore, if S waves from an earthquake are not detected beyond a certain angle from the epicenter, it implies that they must have encountered a large, liquid region deep inside the planet. This observation was crucial in confirming the existence of the liquid outer core. P waves, which can travel through liquids, also have a shadow zone, though it is smaller and caused by the refraction of waves as they pass through the liquid outer core and then the solid inner core, bending them away from certain surface areas. These shadow zones are not just curiosities, they are direct fingerprints of Earth's internal architecture. The history of these discoveries is a testament to persistent scientific inquiry. The first major breakthrough came in 1909 from a Croatian seismologist named Andrija Mohorovičić. Analyzing data from a local earthquake, he noticed something peculiar. Two sets of P waves arrived at seismograph stations, one traveling directly through the crust, and another, faster set, that appeared to have traveled through a deeper, denser layer before returning to the surface. This observation led him to propose the existence of a sharp boundary, now known as the Mohorovičić discontinuity, or simply the MOHO, which marks the transition from the Earth's crust to the underlying mantle. This boundary typically lies at depths ranging from 5 to 10 kilometers beneath oceanic crust and 30 to 50 kilometers beneath continental crust, acting as the fundamental division between our familiar surface and the vast unknown depths. A few years earlier, in 1906, British seismologist Richard Dixon Oldham provided the first clear evidence for a central core. By observing the P-wave shadow zone, he deduced that Earth must have a massive, distinct central region that significantly altered the paths of seismic waves. Then, in 1913, German seismologist Benno Gutenberg refined these observations, determining the depth of this core mantle boundary to be approximately 2,900 kilometers below the surface. This was a remarkable achievement, defining the colossal boundary that separates the rocky mantle from the metallic core, a boundary that still stands as accurate today. Perhaps one of the most elegant and profound discoveries was made in 1936 by Danish seismologist Inge Lehmann. Studying seismic records from a large New Zealand earthquake, she noticed faint P waves arriving within the P wave shadow zone, a region where they should not have been detected according to the existing models of a solely liquid core. Lehmann hypothesized that these waves must have been reflected or refracted by an even deeper, solid inner core within the liquid outer core. Her meticulous analysis and bold deduction unveiled the inner core, a solid sphere at the very center of our planet. This discovery dramatically reshaped our understanding of Earth's deep interior, adding another layer of complexity to its already intricate structure. How incredible is it that a single, subtle anomaly in seismic data could reveal such a monumental truth about our planet's heart? Modern seismology has moved far beyond simply identifying layers. Today, scientists use sophisticated techniques like seismic tomography, which is conceptually similar to a medical CT scan. Instead of just looking at reflections, seismic tomography analyzes millions of seismic wave travel times from countless earthquakes recorded by global networks. By observing subtle variations in wave speed, where waves travel slightly faster or slower than average, scientists can create three-dimensional images of the Earth's interior. Faster wave speeds generally indicate colder, denser, or more rigid material, while slower speeds suggest warmer, less dense, or more molten regions. This allows researchers to visualize dynamic processes within the mantle, such as the descent of cold tectonic plates into the deep Earth at subduction zones, or the ascent of hot plumes of rock from the core mantle boundary towards the surface, which are thought to fuel hotspots like Hawaii. Beyond earthquakes, another powerful tool comes from studying Earth's normal mode oscillations. After very large earthquakes, the entire planet can literally ring like a bell. These subtle, long-period vibrations, or normal modes, provide information about the Earth's bulk properties, its overall density, elasticity, and the distribution of mass within its various layers. Analyzing the frequencies and decay rates of these global oscillations offers complementary insights into the planet's deep structure, independent of direct wave travel times, further validating and refining our models. To further confirm and understand what seismic waves are telling us, scientists also conduct extreme laboratory experiments. Using devices like diamond anvil cells, they can subject tiny samples of minerals to pressures up to several million atmospheres and temperatures reaching thousands of degrees Celsius, replicating the conditions found deep within the Earth. By observing how minerals behave under these extreme conditions, how they transform, what their densities are, and how seismic waves would pass through them, they can better interpret the seismic data. For instance, these experiments have been crucial in confirming that minerals like ringwoodite can indeed hold significant amounts of water within their crystal structures under mantle conditions, providing a physical basis for the seismic anomalies observed in the transition zone. These combined approaches, seismology, laboratory experiments, and sophisticated computational models running on supercomputers, have allowed us to piece together the extraordinary story of Earth's interior. Remember the discussion of oceans hidden in the mantle? Seismic waves played a critical role in that discovery. In the mantle's transition zone, roughly between 410 and 660 kilometers deep, seismologists observed anomalies in wave speeds that were difficult to explain with dry rock models. Some regions showed slightly slower P waves and faster S waves, or vice versa, depending on the specific depth and material. These subtle variations suggested the presence of something unusual. It was hypothesized that these anomalies could be explained by the presence of water trapped within high-pressure minerals like ringwoodite. Laboratory experiments then confirmed that ringwoodite, under the immense pressures and high temperatures of the transition zone, has a unique crystal structure capable of incorporating hydroxyl groups, essentially water molecules, into its lattice. This wet ringwoodite would indeed alter seismic wave speeds in a way consistent with the observations. However, the direct evidence remained elusive for decades. Then, in 2014, a remarkable discovery provided a tiny, yet incredibly significant piece of direct proof. A rare diamond, formed deep within the mantle at depths of about 660 kilometers and brought to the surface by volcanic activity, was found to contain a microscopic inclusion of ringwoodite. And within this ringwoodite, scientists found tiny pockets of water. This single, extraordinary sample acted as a validation of decades of indirect seismic evidence and laboratory predictions. It confirmed that water can indeed exist in the mantle's transition zone, chemically bound within minerals, supporting the idea that this deep reservoir could be as vast or even vaster than all our surface oceans combined. It was a moment of profound scientific confirmation, connecting the abstract models of seismic data to a tangible piece of Earth's hidden interior. Does it not fill you with wonder to think that a tiny speck within a diamond could reveal such a colossal secret about our planet? Even with these incredible tools, the exploration of Earth's interior remains an active and challenging field. Scientists continue to refine seismic tomography models, striving for ever higher resolution, much like improving the clarity of a blurred photograph. They are also investigating phenomena like anisotropy, where seismic waves travel at different speeds depending on their direction of travel. This effect, particularly pronounced in the inner core, provides clues about its crystalline structure, its growth history, and even its slow rotation relative to the rest of the planet. Debates continue about the precise composition of the core, Is it pure iron and nickel? Or does it contain lighter elements like silicon, oxygen, or sulfur? These questions are being tackled by combining increasingly detailed seismic data with advanced computational models that simulate the complex fluid dynamics and mineral physics of the deep Earth. Ultimately, our understanding of Earth's interior, built upon these echoes from below, is a testament to human ingenuity. Without ever setting foot inside, we have mapped continents of molten metal, discovered oceans within stone, and charted the fiery heart of our world. This journey into the inaccessible depths, guided by the subtle vibrations of earthquakes, continues to reveal a dynamic, living planet, far more complex and surprising than we could have ever imagined. Each new seismic wave that ripples across the globe carries with it another whisper of Earth's hidden story, inviting us to listen more closely and to understand our home world a little better. We have journeyed deep into our planet, uncovering hidden oceans within its mantle and a fiery core hotter than the surface of the sun. But to truly understand Earth, we must now move beyond merely describing its individual layers and begin to see them as parts of a grand, interconnected system. Our planet is not a static collection of distinct shells. Instead, it is a single, breathing, dynamic entity where the deep interior profoundly influences everything we see and experience on the surface. Imagine Earth not as a series of separate rooms, but as a vast, intricate machine where every gear and lever affects every other part, creating a constant slow-motion ballet of geological forces. How do these unseen deep Earth processes orchestrate the very stage upon which life unfolds? At the heart of this planetary dynamism lies the Earth's mantle, that vast, semi-solid layer extending nearly 2,900 kilometers beneath our feet. Here, immense heat, primarily generated from the decay of radioactive elements and residual heat from Earth's formation, drives a process known as convection. Picture a pot of thick, warm honey on a stove. As the bottom heats up, it becomes less dense and slowly begins to rise. When it reaches the cooler surface, it spreads out, cools, becomes denser, and then sinks back down, creating a continuous, circulating current. The Earth's mantle behaves in much the same way, though on timescales that dwarf human experience. Hot, buoyant plumes of mantle material slowly ascend from near the core mantle boundary, sometimes rising thousands of kilometers over tens of millions of years. As this material approaches the cooler crust, it spreads horizontally, exerting a dragging force on the overlying tectonic plates. These tectonic plates are not just the surface crust. They are vast, rigid slabs of the lithosphere, which includes the crust and the uppermost brittle part of the mantle, extending down to about 100 kilometers in depth. These plates, varying in thickness and composition, ride atop the slowly churning, more ductile asthenosphere, the softer upper part of the mantle. The horizontal movement of the convective currents in the mantle acts like a giant, slow-moving conveyor belt, dragging these colossal plates across the Earth's surface at speeds comparable to the growth of your fingernails, typically a few centimeters per year. This seemingly imperceptible motion, accumulated over millions of years, is responsible for reshaping continents, opening and closing ocean basins, and sculpturing the dramatic landscapes we see today. Can you truly grasp the immense power of a force that can move entire landmasses across the globe, yet operate so slowly as to be almost undetectable without precise instruments? When these tectonic plates interact, geological drama unfolds. At divergent plate boundaries, where mantle convection causes plates to pull apart, molten rock, or magma, rises from the mantle to fill the gap, creating new oceanic crust. This process is most evident at mid-ocean ridges, like the Mid-Atlantic Ridge, a colossal underwater mountain range stretching for tens of thousands of kilometers, where new seafloor is continuously generated. In contrast, at convergent plate boundaries, plates collide. If an oceanic plate meets a continental plate, the denser oceanic plate is forced to slide beneath the continental plate in a process called subduction, plunging back into the mantle. This descent creates deep ocean trenches, such as the Mariana Trench, the deepest known point on Earth, and can melt the descending slab, generating magma that rises to form volcanic mountain ranges along the continental margins, like the Andes in South America. The collision of two continental plates, on the other hand, can create towering mountain ranges, as seen in the Himalayas, where the Indian plate continues to push into the Eurasian plate, slowly lifting the highest peaks on our planet. These plate interactions are not always smooth. They build up immense stress in the Earth's crust. When this stress overcomes the strength of the rocks, it is released suddenly as an earthquake, sending seismic waves rippling through the planet. The vast majority of earthquakes and volcanic eruptions occur along these plate boundaries, serving as powerful reminders of the restless energy deep within the Earth. Without these deep mantle currents, our planet would be a very different place. The land masses would be static, the crust would not be recycled, and the constant geological renewal that shapes our world and influences its climate would cease. Would a static Earth, devoid of these powerful internal forces, be capable of supporting the same diverse and dynamic life we see today? But the mantle's influence doesn't stop at shaping the surface. It also plays a crucial role in regulating Earth's long-term climate. Plate tectonics acts as a fundamental component of the planet's carbon cycle. Volcanic eruptions release carbon dioxide into the atmosphere, while the weathering of rocks and the subduction of carbon-rich sediments remove it. This delicate balance, maintained over geological timescales by the continuous movement of plates, helps to stabilize Earth's surface temperature, preventing it from spiraling into either a runaway greenhouse effect or a permanent ice age. It's a testament to the profound interconnectedness of Earth systems that processes occurring thousands of kilometers beneath our feet can have such a direct bearing on the air we breathe and the climate we experience. Even deeper, at the very heart of our planet, the liquid outer core performs another vital function for life on Earth. It generates our planet's protective magnetic field. This incredible phenomenon, known as the geodynamo, arises from the convective motion of molten, electrically conducting iron and nickel within the outer core. Imagine this vast ocean of superheated metal, nearly 2,300 kilometers thick, slowly swirling and churning under extreme pressure and temperature. As this conductive fluid moves, it generates electrical currents, much like a dynamo in a power plant. The Earth's rotation, through the Coriolis effect, twists these convective currents into helical patterns, amplifying the electrical currents and, in turn, strengthening the magnetic field they produce. This creates a self-sustaining feedback loop, a cosmic engine of immense power. This magnetic field extends far beyond Earth's solid surface, stretching thousands of kilometers into space, to form a protective bubble called the magnetosphere. This invisible shield is absolutely critical for life. The Sun constantly emits a stream of charged particles known as the solar wind, traveling at speeds of hundreds of kilometers per second. Without a strong magnetic field, these energetic particles would relentlessly bombard Earth's atmosphere, slowly stripping it away over geological time, much like what is believed to have happened to Mars, which lost its global magnetic field billions of years ago. Our magnetosphere deflects most of the solar wind, channeling these harmful particles around the planet. Only a small fraction manages to penetrate near the magnetic poles, where they interact with atmospheric gases, creating the breathtaking displays of the aurora borealis and aurora australis, the northern and southern lights. Beyond shielding us from deadly radiation, the magnetic field also plays a more subtle but equally important role. For centuries, humanity has relied on compasses for navigation, guided by the Earth's magnetic poles. Many animals, from birds to sea turtles, also possess an innate magnetic sense, using the planet's field for long-distance migration. The geodynamo is not static. It is constantly changing. The magnetic poles drift over time, and even more dramatically, the entire field occasionally reverses its polarity, with the north and south magnetic poles swapping places. These reversals have occurred hundreds of times throughout Earth's history, with the last major reversal happening about 780,000 years ago. During a reversal, the field weakens significantly, potentially leaving Earth more vulnerable to solar radiation for a period of several thousand years. This dynamic nature of the geodynamo reminds us that even our planet's most fundamental protective mechanisms are in a state of continuous flux. These deep Earth processes directly challenge common misconceptions about our planet. Many people imagine Earth as a solid, unchanging sphere, perhaps with some surface activity. Yet, the reality is far more vibrant and complex. The idea of a static Earth is fundamentally incorrect. Our planet is a living, breathing entity, constantly rebuilding itself from within. From the slow dance of continents driven by mantle convection to the invisible shield generated by the core, these internal dynamics are not just interesting scientific facts. They are the very foundation of Earth's long-term habitability. They regulate our climate, protect us from solar radiation, and continuously renew the crust, providing the raw materials and environments necessary for life to thrive. The profound interplay between the core, mantle, and crust creates a planetary system that is robust yet delicate, stable yet constantly evolving. The heat radiating from the inner core drives the convection in the outer core, generating the magnetic field. This field, in turn, protects the atmosphere that is shaped by the mantle's convective currents, which drive plate tectonics. Plate tectonics then influences volcanism, which releases gases that affect the atmosphere, further influencing weathering and the carbon cycle. It's a continuous, interconnected feedback loop, a symphony of geological forces that has been playing for billions of years. Understanding this intricate dance allows us to appreciate the true wonder of our home world and the remarkable conditions that allow life to flourish. Our journey has taken us to the very heart of our planet, a voyage not of rockets and telescopes, but of scientific ingenuity and profound imagination. We've descended through the familiar soil and rock, past the churning, water-rich mantle, and into the searing, high-pressure realm of the Earth's core. We have seen how our world is not a static sphere, but a vibrant, living entity, constantly in motion, shaping itself from the inside out. Yet, as with any grand exploration, the further we delve, the more we realize the vastness of what remains unknown. The journey into Earth's interior is far from over. It is a continuous quest, pushing the boundaries of human understanding. What incredible secrets might our planet still hold, hidden just beyond the reach of our current knowledge? Even with the remarkable insights gained from seismic waves and high-pressure experiments, scientists are still striving to refine their models of these hidden depths. Consider the mantle's watery secret, the vast reservoirs of water locked within minerals like ringwoodite. While we have compelling evidence for its existence, the precise volume of this deep Earth ocean remains a subject of active research and ongoing debate. Is it truly 1, 2, or even 3 times the amount of water found in all our surface oceans combined? Pinpointing this figure requires even more detailed seismic tomography, searching for subtle variations in wave speeds that might indicate areas of higher hydration. Laboratory experiments continue to play a crucial role, mimicking the extreme pressures and temperatures of the deep mantle, allowing researchers to study how various minerals, including ringwoodite, wadsleyite, and even denser phases, incorporate and release water under these conditions. These experiments help us understand the plumbing system of our planet, how water moves through its interior, influencing everything from the fluidity of the mantle to the generation of volcanic melts. Imagine the sheer effort involved. Scientists meticulously designing apparatus that can generate pressures equivalent to hundreds of thousands of atmospheres, heating tiny samples to thousands of degrees Celsius, all to observe how a few atoms of hydrogen and oxygen behave within a crystal lattice. Each successful experiment, each new seismic dataset, acts as another brushstroke on the incomplete portrait of our planet's interior. This ongoing work isn't just about curiosity, it deepens our understanding of the entire global water cycle, a cycle that extends far beyond the clouds and oceans we see, reaching deep into the very stone beneath our feet. How much of Earth's primordial water might still be trapped down there, slowly cycling? And what does that tell us about the planet's long-term evolution? Further down, the Earth's core presents its own set of profound mysteries. While we know it is primarily composed of iron and nickel, the precise percentage of lighter elements, such as sulfur, silicon, oxygen, or even hydrogen, remains an active area of investigation. These seemingly minor constituents can have a major impact on the core's density, its melting point, and ultimately the dynamics of the geodynamo that generates our magnetic field. Scientists use sophisticated computational models, running for months on supercomputers, to simulate the turbulent flow of liquid metal in the outer core, trying to match the observed magnetic field patterns and its historical changes. These simulations are incredibly complex, factoring in Earth's rotation, heat flow, and the subtle interactions between different layers. The solid inner core, too, is not without its enigmas. Seismic studies have revealed that it exhibits a property called anisotropy, meaning seismic waves travel faster when moving parallel to the Earth's rotational axis than when traveling perpendicular to it. This suggests a preferred orientation of iron crystals within the inner core, but the exact mechanism for this alignment is still debated. Some theories propose that the immense pressure and the slow, creeping deformation of the solid iron are responsible, while others suggest it relates to the growth process of the inner core itself. There's even the intriguing hypothesis of an inner core, a distinct structure within the already solid inner core, hinted at by subtle seismic reflections. If confirmed, this would add yet another layer of complexity to our planet's deepest regions, a nested Russian doll of planetary structure. What could possibly differentiate this innermost sphere from the rest of the inner core? And what forces could have shaped it? The core mantle boundary, often referred to as the D layer, is another frontier of intense study. This dramatic interface, where the molten iron of the outer core meets the solid silicate rock of the lower mantle, is a region of extreme temperatures and pressures and profound chemical reactions. It is believed to be a dynamic zone where heat exchange is vigorous, influencing both mantle convection and core dynamics. Some scientists hypothesize that this boundary is not smooth, but rather exhibits large-scale topographic variations, like mountains and valleys, formed by the interaction of rising mantle plumes and downwelling slabs of subducted crust. Understanding this boundary is critical, as it acts as the primary heat regulator for the entire planet, affecting everything above it. This relentless pursuit of knowledge about Earth's interior is not merely an academic exercise. It carries profound practical significance for humanity. A deeper understanding of plate tectonics, driven by mantle convection, directly informs our ability to assess and mitigate natural hazards. While we cannot predict specific earthquakes or volcanic eruptions with precision, knowing the underlying mechanisms and stress accumulation rates in different regions helps us to identify high-risk zones, improve building codes, and develop early warning systems where possible. For instance, understanding how water influences magma generation in subduction zones could lead to better models for volcanic activity. Every tremor, every eruption is a whisper from the deep, and scientists are constantly working to decipher its message. Our planet's magnetic field, generated in the outer core, is another critical link between the deep Earth and our everyday lives. This invisible shield protects us from the constant barrage of harmful charged particles from the Sun, known as the solar wind, and from more energetic cosmic rays. Without it, our atmosphere would likely have been stripped away over billions of years, much like what happened to Mars. Understanding the dynamics of the geodynamo is crucial for predicting space weather events, such as severe solar storms, which can disrupt power grids, disable satellites, and interfere with global communications and navigation systems like GPS. Imagine a world without satellite communication or widespread power outages. The economic and social impact would be immense. Current research into magnetic pole reversals, which have occurred many times throughout Earth's history, seeks to understand their frequency, duration, and potential environmental consequences, even if the direct risks to humanity during a reversal are still debated and likely less dramatic than often sensationalized. How stable is our magnetic shield, and what would a prolonged period of weakened magnetic field mean for our technological civilization? Beyond immediate hazards, knowledge of Earth's interior is fundamental to understanding the long-term evolution of our planet's climate and its habitability. Plate tectonics plays a vital role in the global carbon cycle, slowly recycling carbon from the atmosphere and oceans into the mantle and releasing it back through volcanic activity. This geological thermostat has helped regulate Earth's climate over millions of years, preventing runaway greenhouse effects or deep freezes that could render the planet uninhabitable. The presence and movement of water within the mantle also influence these processes, affecting the chemistry and dynamics of volcanic outgassing and the formation of carbonate rocks. By studying Earth's deep past, encoded in its rocks and magnetic record, we gain insights into its future, offering a clearer picture of the delicate balance that sustains life. Furthermore, our understanding of Earth's internal workings provides a crucial framework for studying exoplanets, worlds beyond our solar system. When astronomers discover a new rocky planet, one of the first questions is often about its potential for habitability. Does it have a molten core? Is it geologically active? Does it possess a magnetic field? The lessons learned from our own Earth about the interplay between internal heat, plate tectonics, and a protective magnetosphere become invaluable guides in the search for life elsewhere in the cosmos. Earth serves as our primary laboratory for planetary science, a detailed case study of a living world. The journey into Earth's interior is a testament to human ingenuity and the enduring spirit of scientific inquiry. We cannot send probes to the core, nor can we drill more than a few kilometers into the crust. Yet through indirect methods, clever experiments, and powerful simulations, we have built a surprisingly detailed picture of this hidden realm. New seismic observatories are constantly being deployed, gathering ever more precise data. Advancements in computational power allow for increasingly realistic simulations of mantle convection and core dynamics. The study of rare, deep-source diamonds continues to offer tantalizing direct samples from the mantle, sometimes even containing minerals that formed under extreme pressure, far beneath our feet. These tiny, precious inclusions are like messages in a bottle, carried from the abyssal depths to the surface, offering direct chemical insights into the mantle's composition. So, as we conclude this exploration, remember that our planet is a world of endless wonders, a dynamic masterpiece of physics and chemistry unfolding over billions of years. From the thin, vibrant crust we inhabit, to the churning, water-rich mantle, and the fiery, solid heart hotter than the sun's surface, every layer tells a story of immense power and intricate balance. The earth beneath our feet is as alien and fascinating as the farthest reaches of space, and in many ways, even more intimately connected to our daily existence. Our journey may end here, but the scientific exploration of our homeworld continues, inviting new questions, new discoveries, and an ever-deepening appreciation for the extraordinary planet we call home. The greatest adventure, it seems, sometimes lies not in looking out, but in looking down into the very core of our being. What further marvels await discovery in the profound depths of our own world?